Hi, so in this video we're going to talk about parametric differentiation, and that is when we have a function that is sometimes better expressed as another parameter, hence the name parametric differentiation. So you could think of it as, in this case, when it's polynomials, usually the extra parameter is t. In trig functions it is often theta, you can see that. So you could think of this as projectiles in motion. So it is you've got a way of describing the projectile in motion along the x-axis in relation to t, which could be time, and you've also got the function relating it in terms of the y-axis. Okay, so in terms of that, we're going to want to find out the derivatives in order to find the gradients, or rather not the gradients, but specifically the velocity and then the acceleration. So it's a way in which we can have functions in another parameter and still differentiate them. Okay, so this is a bunch of theory, but the important thing is these formula are not given in the exam. Okay, it's derived from the chain rule for both of them. So if you have a function x in terms of t and a function y in terms of t, the derivative f dashed x will be dy by dt times dt by dx. So the derivative of the y function in relation to t and the derivative and the in reciprocal of the x function differentiated in relation to t. But simply put, it is derivative of the y function divided by the x function once they've been differentiated with respect to t, which you can see if you want to look into more detail about that, which is what happens. The second derivative is a bit more complicated, and it's just basically algebraic manipulation of the derivatives. And so what we need to do, and this is a derivation of it simplified, is we differentiate with respect to t our first derivative and divide it by the x derivative with respect to t. It's very complicated to describe that, and hopefully what you'll see is in practice it is actually not too difficult, okay, as long as you're remembering the method. Okay, so calculate dy by dx and d squared y by dx squared for the following pairs of parametric equations. So this could be like a polynomial like I've just described. Well, that's not a polynomial. So first thing we need is to differentiate both of them with respect to t. So it's just regular differentiation. Differentiate that with respect to t, we get 2t. That disappears. Differentiate a log function times the derivative that's inside the brackets. And then in order to get dy by dx, if you remember, it is going to be dy by dt all divided by dx by dt. So we get 3 over 3t plus 2 all divided by 2t. It's not the most nice way of describing that. So we end up with 3 over 6t squared plus 4t. Okay. And that's the first derivative. We also want the second derivative. So we need to firstly differentiate this with respect to t. And then divide it by the dx over dt. Or again, times it by 1 over 2t. Okay. So we're going to have to differentiate that. There we go. So I go through it again. Brought that up. Times by -1, take away from the power, and then times by the derivative of what's inside the brackets. So we got 12t plus 4, and then divided it all by this, the 1 over 2t, multiplied by 1 over 2t, and then simplified it. Okay? So that was finding the second derivative when it's in terms of t, but also it can be trig. And so we want to find the derivative and the second derivative of these two functions. So this is trig, so it's angles. It's in theta rather than t, but nothing changes. We still need to find, first of all, dx, but instead of t, it's going to be d theta. Derivative of sec is sec tan, so we get 2 sec theta tan theta. dy by d theta will be 3 cos theta. Okay? So to get dy by dx, we do 3 cos theta, all divided by 2 sec theta tan theta. Okay? Now what we could actually do is simplify this before differentiating it further, remembering hopefully that sec theta is just 1 over cos theta. So 1 over sec theta will be cos theta. Remembering that tan theta is sin theta over cos theta. So 1 over tan theta, which is this, what we've got here, is going to be cos theta over sin theta. So this inevitably, don't know why I said that, will turn into 3 over 2. That sec theta will become a cos theta, so it's cos squared theta. And that tan theta on the bottom will become a cos theta over sin theta. So it eventually, I think that's the word I was going for, and came up with inevitably 3 cos cubed theta over 2 sin theta. Okay? Now I want to get the second derivative. So I differentiate that with respect to theta. And then times it by 1 over 2 sec theta tan theta. Okay? So quotient rule, differentiate top. So we're going to get 9 cos squared theta times the derivative inside the brackets, which is going to be negative sin theta, 2 sin theta, minus 3 cos cubed theta times that derivative, which will be negative 2 sin 2 cos theta. Nope, don't know where the negative came from. It's just going to be 2 cos theta all over 2 sin squared theta. And that's going to be multiplied by 2 sec theta tan theta. I'll rewrite that later. So we've got negative 9 times 2 will be negative 18. Got a cos squared theta, a sin squared theta. We have a 6 cos to the power 4 theta all over 4 sin squared theta tan theta. Okay. So let's see if this can simplify. I'll rewrite it on the top of the other page. So 4 times the 2. And then we can see if we can simplify any further. We know that tan theta equals sine over cos. Sec theta equals 1 over cos. So we can get negative 18 all over sec theta is 1 over cos. And tan theta is sine theta over cos theta. Sine squared, so it's going to be 8 sine cubed theta all over cos squared theta. So we're dividing by that, so that cos squared, so it's going to be times by the reciprocal, so the cos squared is actually just going to come up onto the top. Yep. So we get negative 18 cos to the power 4 theta sine squared theta minus 6 cos to the power 6 theta all over 8 sine cubed theta, because that would flip. Yep. Then let's see if anything else can happen. Probably. However, it's all in sines and coses, which means if I was to put that into a calculator, I'd be able to do it, whereas previously it was in secs and stuff, so I wouldn't be able to do it. So that's as far as I'm going to take it. So that is how we get parametric derivatives, single and double derivatives.